This meeting is being recorded.
In this next section, we're going to review molecular geometry, so section 1.11, and I alluded to molecular geometry in our last video when we talked about bond hybridization and the shapes of the molecules that result. So we're going to review here with Vesper theory. So if you've forgotten, that stands for this valence shell electron pair repulsion, because we know that like charges tend to repel, so electrons will repel one another at the same time. There's the overlap and bond formation. So let's look at things in terms of organic chemistry now. So before, you might have referred to what's called here the steric number as the electron pairs or the electron domains. So now we're going to call these the steric number. And we'll talk about other things that have this word steric in them later on in the semester. But for now, when we have a bond or a lone pair, we're going to add them together. So in this first molecule, methane here, we have 4 bonding pairs, 4 sigma bonds specifically. And that gives us a steric number of 4. In our second molecule, ammonia, we have 3 sigma bonds. So that's a 3 plus 1 lone pair. So we have 3 plus 1 gives us 4, so same steric number. And then last but not least, we have a water molecule here with the same steric number of 4, but that comes from 2 bonding pairs and 2 lone pairs. So if you remember, just because we have the same kind of starting point here, the same steric number, does not mean that all of these molecules will have the same molecular geometry, the same resulting shape. That is dependent on the lone pairs kind of repelling these bonded pairs even more. So we have two lone pairs here with this hydrogen. The way that it's oriented, it looks like it would be a linear, but we're going to see more like this is actually the molecular geometry shape of our water molecule, more of a bent shape. So let's take a look. Let's hopefully you remember some of this information from general chemistry, but it's definitely a good idea to review if you don't. Now we're going to look at all the steric numbers here. So steric number 4 is up first. So we have all 3 of these molecules that we looked at on the last slide listed down here. So we have sp3 hybridization of this central atom, whether it's the nitrogen, the carbon, or the oxygen. So there's 4 orbitals that need to be created, 4 degenerate orbitals, and that would mean that we need sp3 hybridization. If the steric number is 3, we only need 3 degenerate orbitals, sp2. And if our steric number is 2, like acetylene was, right, we would have sp hybridized orbitals. So let's take a look at a little bit more here. If you recall, methane, they were all bonding, so 4 equal bonding pairs. A steric number of 4 with 4 bonds gives us this tetrahedral electron geometry, or rather, it starts with a tetrahedral electron geometry, and since they're all bonding pairs, this remains tetrahedral as our molecular geometry as well. And then we'll see, right, ammonia is also tetrahedral electron geometry. We have 1 lone pair housed in this sp3 hybridized orbital, and then our water molecule over here, we have 2 sp3 hybridized orbitals that house lone pairs. So you can see that the bond angles are decreasing as we go along and add more and more lone pairs. On the next slide here, you'll see how the lone pairs affect our molecular geometry. So methane, right, our first molecule here, would end up retaining from a tetrahedral electron domain, electron pair geometry, retaining that tetrahedral structure as its molecular geometry. There's no lone pairs pushing things more than the bonding pairs. Then we had our ammonia here, so that's 3 bonding, 1 lone pair. So again, tetrahedral electron geometry, but only the bonding atoms are going to be included in our molecular geometry, so it looks trigonal pyramidal, right? We have that nitrogen with those 3 groups making a pyramid below. Next, we have our bent structure, tetrahedral electron domain for water, but we have bent molecular geometries that result with this 2-to-2 electron pair bonding versus lone pair. And then we have, when we only have 3 electron domains total now, so we're going to this molecule, boron trifluoride, BF3, the steric number is now 3, so that's different. And this results in a structure that we would call trigonal planar. So the boron's kind of in the middle, 3 fluorine atoms are surrounding, and it's planar because they would all be in the same plane, and trigonal because, right, if we connect all these lines, right, we have 3 things bonded, it kind of looks like a triangle. So trigonal planar with 3 bonding and 0 non-bonding. The molecular geometry remains the same. You should recall that trend when there's no bonding pairs, the molecular geometry is the same as the electron geometry. So I was looking ahead, our last molecule, BeH2, has 2 bonding pairs, right? Steric number of 2, that would be linear. And since we have no lone pairs possible, the molecular geometry would also be linear. All right, so again, the importance of lone pairs, the bond angles change. They get smaller and smaller from our original 109.5 tetrahedral. This was that boron trifluoride. You'll notice that if we draw a circle here, we know that that has 360 degrees. 360 degrees. If we divide that by 3, that's where we get that 120 bond angle here for trigonal planar molecular geometry. It's electron geometry. The molecular geometry is the same. All right, so we should go back real quick and remind ourselves that sp2 hybridized would be what's needed for boron to form 3 degenerate bonds. And then we had our example of steric number 2. So we have, with this molecule, a linear shape. So if we draw a circle, right, with the line down the middle here, we would divide it in half. So that's where the 180-degree bond angle comes from. If you want to practice drawing CO2, if you started with the number of valence electrons and worked through, you should end up with a structure like this, right? So everybody has a full octet. These are now double bonds, but this is also a linear molecular geometry that results. And they ask you about p orbitals. So think about the number of bonds that are needed and if any p orbitals will be left over unhybridized. And the last slide here kind of sums up all of the steric numbers, right? So we'll start there. And then you're given the the hybridized orbital that's needed to form that number, right, of 4 degenerate bonds. Then here we're given the arrangement of the electron pairs or the electron domain geometry you might have been taught. And if there's no lone pairs, this is where we ask the last question in this flowchart. The same geometry, right, that we looked at up here for our electron geometry would result for our molecular geometry. 1 lone pair, so tetrahedral, tetrahedral for no lone pairs. 1 lone pair, tetrahedral electron geometry, trigonal pyramidal, right? Imagine those electrons there. And then we have our bent when we have 2 lone pairs. So I would take a look at this slide for a good summary of section 1.11, and we will continue with 1.12 with the next video.